Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to extend our discussion of math induction to something called strong induction. Now, with math induction, you try to prove that if an nth proposition is true, then the n plus first proposition is also true. That's the induction trigger. And you also need to show that the first proposition is true. So the induction trigger will then instigate a domino effect, which will demonstrate that an infinite sequence of propositions is true. Strong induction is a little bit different. Here, of course, you need to show that at least one proposition is true, but you also need to show that if the first several propositions are true, that implies that the n plus first proposition is also true. And then you conclude that for all k, an element of the set of natural numbers, the kth proposition will be true. So it'll be true all along the line. So before, we only had p of n implies p of n plus 1. With strong induction, you assume that all of the preceding propositions are true and use that to imply that the n plus first proposition is also true. You still get this domino trigger because it includes the case of just regular math induction. But here you're assuming all of these propositions are true and their truth implies the truth of the next proposition. Let me give you an example. Show that if n is an element of the set of natural numbers, n strictly greater than 1, then n can be written as a product of primes. The proof will, of course, be by strong induction, as you shall see. And hopefully this example will illustrate the need for strong induction in some circumstances. So, for the first part, notice that its natural number is bigger than 1. So the first proposition is p of 2, and that's n equals 2. Can 2 be expressed as the product of primes? Well, yeah, 2 is 2, and that's a prime, so it's expressed as a product of primes in the sense that all the factors are primes. In the second part, we're going to suppose that all numbers up to n are expressible as a product of primes. They have a prime factorization. Now we're going to consider n plus 1. There are two possible cases. Either n plus 1 is prime, in which case it is a product of primes, or n plus 1 is composite. Say n plus 1 is equal to a times b. A and b, element of the set of natural numbers, a and b greater than 1. Then by the strong induction hypothesis, A and B are expressible as a product of primes. You might see now why that strong induction hypothesis was necessary. It's not sufficient to only know that n is expressible as a product of primes, because n plus 1 is expressible as a times b. Who knows what those are? For instance, if n plus 1 is 6, then a and b would be 2 and 3. Neither of those refers to the number 5. So knowing that 5 is a product of primes is not sufficient to show that 6 is. You have to know that all the numbers smaller than 5, smaller than or equal to 5, are products of primes in order to show that 6 is. So a and b are a product of primes. Thus, n plus 1, which is a times b, is expressible as a product of primes. And so this gives us the ability to make the conclusion then that all natural numbers are expressible as a product of primes as long as n is greater than or equal to 2. In our next example, I want to show, which means prove, that every postage amount worth greater than or equal to 12 cents can be formed using 4-cent and 5-cent stamps. So 4-cent and 5-cent stamps are sufficient to form any postage value greater than or equal to 12 cents. In our proof, by strong induction, we first have to show that 12-cent stamps can be expressed using 4-cent and 5-cent stamps. And 12 cents is 3 times 4 cents, and so 12-cent stamps surely can be produced with 4-cent and 5-cent stamps. So in the second part of our proof, we're going to assume P of 12, P of 13, up to P of n are true, which means 12, 13, up to n cent stamps can be expressed with 4-cent and 5-cent stamps. Now we need to consider the next case, the n plus 1 case. How can we show that this assumption implies that n plus 1 value postages can be expressed using 4-cent and 5-cent stamps? And the proof goes like this. If n plus 1 is a multiple of 5, then done. It can be expressed as some constant times the 5-cent stamps. Suppose n plus 1 is not a multiple of 5. Then when you take the n plus 1 and you divide it by 5, you get some quotient plus a remainder which is not 0. The remainder will be a number greater than or equal to 1 and less than or equal to 4. So you can see that n plus 1 is expressible as some 5 times the quotient plus the remainder. Now note that 4 and 5 are relatively prime. So you can construct numbers like r as constants times 4 plus another constant times 5, but the catch being c1 and c2 are elements of the set of integers. So they could be negative. However, keep in mind what values c1 and c2 can possibly have. If the remainder is 1, then you'll choose c2 to be 1 and c1 to be negative 1. If r is 2, you can choose C2 to be 2 and C1 to be negative 2. For r equals 3, you can choose C2 to be 3 and C1 to be negative 3. And finally, for r equals 4, you can choose C1 to be 1 and C2 to be 0. So these numbers, C1 and C2, can't be any lower than negative 3. And in all of those cases, the only one that was ever negative was C1. We can substitute this into the equation down here. So that n plus 1 is now 5 times q plus C1 times 4 plus C2 times 5. And that gives you 5 plus C2 times 5 plus C1 times 4. The one remaining step is we had to show that we could calculate these postages using 4-cent and 5-cent stamps, and you can't use a negative number of stamps. So we have to deal with the case where C1 is negative. So if C1 is minus 1, how can we construct negative 4 using 4 and 5? And the answer is we can take 4 times those 4-cent stamps and subtract 4 times the 5-cent stamps. So what would happen if we replace that up here? And so we get n plus 1 is, here's your 5 plus C2 times 5, and C2 is always bigger than or equal to 0. And this negative 4 is going to be 4 times 4-cent stamps minus 4 times 5-cent stamps. And so what you end up with is 1 plus C2 times your 5 cents plus 4 times 4 cents in that case where C is equal to negative 1. There's two other cases to consider. If C2 is negative 2, then notice that negative 2 is equal to 2 times your 4-cent stamps minus 2 times your 5-cent stamps. And so again, n plus 1 will be 5 plus C2 times 5 plus 2 times your 4-cent stamps minus 2 times your 5-cent stamps. And that gives you then 3 plus C2 times 5 plus 2 times 4. Again, coefficients now positive, so you can use your 4 and 5-cent stamps to construct n plus 1 in this case. Now there's only one case left. If C1 is negative 3, notice that negative 3 is equal to 3 times 4-cent stamps minus 3 times 5-cent stamps. So you get your negative 3 out of that. So therefore, n plus 1 will be 5 plus C2 times 5 plus this 3 times your 4-cent stamps minus 3 times your 5-cent stamps. So that's going to be 2 plus C2 times 5 plus 3 times 4. And that shows then that in all cases you can use positive coefficients, a positive number of 4-cent and 5-cent stamps, or 0, in order to construct n plus 1 valued stamps, provided that you can do the same for n valued stamps. We're next going to look at an interesting problem in computational geometry instead of arithmetic. We begin with the definition of a polygon. So this might be a polygon. What is a polygon? A polygon is a sequence of line segments and each one begins where the previous one left off. So if this one leaves off here, this one will begin here. With each line segment beginning where the previous one left off. And one more thing, it has to be closed. It can't be something like this where it doesn't close up. It actually has to close up. And the last line segment ends where the first line segment began. And so that's what a polygon is. You should note that things like this we will consider to be a single polygon. Yeah, it kind of has sides that self-intersect, but still we'll call it a polygon. And things like this are not polygons because it's not closed. A polygon is called simple. It's a simple polygon if none of its line segments intersect. Of course, except the starting and stopping points. Point, actually. So this is not simple. And this is simple. A polygon is convex if every pair of points on the region enclosed by the polygon may be connected by a line segment that lies in the interior region. So let me give you an example. Suppose I have something like this. This is not convex because if I take these 2 points and connect them by a line segment, the line segment leaves the region. So this is not convex. Whereas something like this is convex. Any 2 points inside can be connected by a line segment that lies entirely in the interior region. A diagonal of a polygon is a line segment between 2 non-adjacent vertices of the polygon. So if I have a polygon like this, then the line segment here would be one of its diagonals. You can see there would be a large number of possible diagonals here. Finally, a triangulation of a polygon is a division of the polygon into triangles by use of non-intersecting diagonals. So again, if I have this is my polygon, how can I triangulate it? I'll slice it here, and then I'll slice it here. And now I've divided this pentagon into 3 triangles. So it has now been triangulated. We have the following theorem. Every simple polygon can be triangulated. With, of course, non-intersecting diagonals. I should also add, if n is bigger than or equal to 3, which it must be for a closed simple polygon, then we may use n minus 2 triangles in that process of triangulation. The proof is based upon the following lemma. Every simple polygon having n greater than or equal to 4 edges or vertices has an interior diagonal. So if you are a simple polygon and you have 4 or more vertices, then there is an interior diagonal. So in the proof of our previous theorem, let V1, V2, Vn be vertices. So by way of visual aid, let's suppose we have V1, V2, V3, V4, and V5. Use line segment. Use the line segment from V1 to V3 as your interior diagonal that divides the region up into a triangle plus a new polygon. Then V1, V3, V4, V5 is a polygon having 1, 2, 3, 4. It's going to be n minus 1 vertices. This being smaller by induction, this latter polygon may be triangulated with n minus 3 triangles. But that means the original triangle can be the original polygon can be triangulated with one additional triangle. Triangulate the original polygon. Both math induction and strong induction are based upon an important mathematical principle called the well-ordering property. What is the well-ordering property? Every non-empty a subset of the natural numbers has a least element. This ends up being a very important property in mathematics. We're going to provide a proof of math induction using the well-ordering principle. So in our proof, we're going to suppose proposition 1 is true, and the truth of proposition n implies the truth of proposition n plus 1. Let S be the set of all natural numbers n such that P of n is false. So those are the fails for the proposition in question. Then by the well-ordering principle, S has a least element, and we're going to name it as n caret, kind of the least element by n with this little lower aiming wedge. Well, this is the smallest element for which the proposition is false, which means the proposition at n wedge minus 1 is true, but we have this induction trigger. That implies P of n wedge is true, and that's a contradiction because it's supposed to be the least element amongst all those values where P of n is false. We deduce then that S is empty. It has no elements, because if it did, it would have a least element, and then that least element would have a prior proposition is true, but then the induction trigger would imply that that particular proposition is also true, and so S has to be empty. And that's the end of the proof.